Hello and welcome to another video. In this video we're going to be working on minimum number of pushes to type word 1, and then we're going to be doing the medium follow-up that were both on this week's weekly contest. They're very similar problems. We're going to get a generic solution for this one, and then we'll go to the next one. So in the problem you're given a string word containing lowercase English letters. And telephone keypads have keys mapped with keys which can be used to form words. So for example, 2 in a telephone keypad is mapped with ABC. We need to push the key 1 time to type A, 2 times to type B, and 3 times to type C. So basically where the letter is in the keypad is how many times you have to push it. So because A is in the front, if you push if you push 2 once, it'll give you A. If you push 2 twice, it'll give you B, and 3 times for C. You're allowed to remap these keys to whatever you want. The keys can have any number of letters, but each letter must be mapped to exactly 1 key, and you need to find the minimum number of times the keys will be pushed to type the string word. Return the minimum number of pushes needed to type word after remapping the keys. An example remapping of the keys to the letters is given below. Notice that 1 and these 2 things can't be mapped to anything. And 0 as well. So we can only map to 2 through 9. So here's an example, and we have A, B, C, D, E. So for A, B, C, D, E, for A we need to push 2 1 time. For B, we need to push 3 1 time. For C, 4 1 time. For 5, D 1 time. And for 6, E 1 time. Or for E, 6 1 time. So we have 5 total key presses, so we return 5. Then here is another word with some mappings, and basically they tell you how much you need to push every single letter. So X looks like is on key 2. Y is on key 2, pushing it twice. C is on key 3, pushing it once. D is on key 3, pushing it twice, and so on. So you basically add up all of these costs of the keys, and the cost of the key is just the order of the key on the number and how many times you need to push that number. So for example, if P is 3rd here, you would need to push 6 3 times to get P. And you can make this ordering anything you want, so you can map every single key to only 1 letter. It's total preference, whatever you want. And they tell you the word length is 26 characters, and the word consists of lowercase English letters, and they're all distinct. So the longest word you can have is just like A through Z in some order. So first we have to figure out like what is a good mapping, right? Like you can kind of tell from this first example if you have some letters, and let's actually just write down a bunch of letters and map our word. So let's just say we have 2, 3, 4, 5, 6, 7, 8, 9, and maybe let's make this a little bit bigger. So these are all of the numbers we can map letters to. So let's say we do have this word right here, up here. Yeah. So, and we need to figure out like how to map this. So our word is going to be this X, Y, C, D, E, F, G, H, I, J. So this is our word we need to map it. So to minimize key presses, ideally you want to have each character, basically the idea is ideally have each character with as small of an index as possible, right? So for example, if X, like if we just put everything on 2, so X would be on 2, like we can write that here. So 2 would have like an X. So this X would have a count of 1 to push, but now if we put a Y, the Y would have 2 operations to push, and then C would have 3 operations, and D would have 4. So this is inefficient. So if we have X here, ideally we want to put Y on another letter, so that way Y also has 1 operation. So the ideal strategy is basically until like you want to put your number, you want to put your letter on a number that has the smallest number of things on it, because that would minimize the amount of pushes it takes to press it. So for example here, we'd want to put X here, Y here, and the word doesn't matter. Like instead of putting X on 2, I can put X on 8 or 9 or whatever. But it basically you just want to be putting things on as many different keys as you can to minimize operations for each one. So you'd put a C here, you'd put a D here, you'd put an E here, you'd put an F here, G, H, right? So your first 8 numbers ideally should go or your first 8 letters should go on different numbers, because that means that the number of operations for these numbers is only 1, right? So if we have the number of operations, the first thing will be 1, the second thing will be 2, the third thing will be 3, and so on. So to minimize the number of operations, to pick the number, you want to spread it out as much as possible. But now that we did, now for I and j, we basically, like, we don't have any more nothings. So we can put these, again, we can put these anywhere here. So you can do something like this and this, or you can put this anywhere, like this wouldn't matter, right? Either way, you're basically going to have two characters that have 2 operations. So you're going to have 8 characters that are 1 operation, no matter how you do it, as long as you put on different ones. And you're going to have 2 characters with 2 operations. So what's the total number of operations? Well, we have 8 characters with 1 operation, plus 2 characters with 2 operations. So total, we have 12. And that's what we get here, right? And so that's kind of like the basic idea of this problem. You want to just spread out your letters as much as you can. But how do we do this without actually keeping track of like what number we put it on? And it's actually pretty easy. So basically what we can do is we can just loop through indices. We don't even care about the letter. We know these are unique. And we know that like every 8 letters, so for example, the first 8 letters we put on will take 1 operation. Then the next 8 letters we put on will take 2 operations. Then the next 8 letters we put on will take 3 operations, and so on, right? Because the first 8 letters will be on the first index, then the second 8 letters will be on the second index, then the third 8 letters will be on the third index, and so on. So we don't even need to like use this. We can just do a basic math problem. So let's say this has, and I think this it tells you, right? So 2, 4, 6. So this has 10 letters. So what we can do is we can make it basically just loop. So if this has 10 letters, we can just loop from 1 to 10 and have some kind of result variable, right? So we'll have a result variable, and then basically in our loop, all we have to do is just figure out like what index is it on. And how do we know what index it's on? We can just divide by 8. So like I said, the first 8 letters will be on index 1, the second 8 letters will be on index 2, and so on. So let's just say we have some random number. Like let's say this word is actually more than 26 characters. Let's say, or actually we can use 26 characters. So let's say we're on character 19. We can just divide by 8. We do a ceiling divide by 8. So you do a ceiling divide, and you will get 3 here. And that means this is on the third index. And that's correct, right? Because the first 8 letters will be here, the second 8 letters will be here, and then you will have 17, 18, 19 will be on index 3. So the letters from index 17 to 26 or 24 will be on 3. And that's basically all you need to do. You just loop. So the generic use case is loop from 1 to num characters plus 1, right? So if you have 10 characters, you would loop from 1 to 10, and then you basically just keep adding, whatever number you're on, so whatever index is on, divided by 8, and you ceiling it because you want to round up. And the reason you want to round up is, like I said, so let's say we're on character number 19. If we rounded down, if we just did like a floor here, we would get 2, but it's not on the second. It's not on the second index. It's on the third index, right? Because the first 8 go here. So 0 to 8, or not 0 to 8, but 1 through 8 go on this index. 9 through 15 go on this index. And then, or it's actually, no, it's going to be 9 through 16. It's going to go on this index. And then here is going to be 17 through 24. And our number is 19, so it happens to be in the 17 through 24 range, which is on the third index. And so that's basically it for this problem. You can just loop you can just loop from 1 to the length of your word and add appropriately. So we can quickly take a look at the code here. And here it is. So you basically just initialize the result to 0. You loop from 1 to the length of the word plus 1 because you want to actually loop to that length of the word. So let's say the length of the word is 10. You want to loop from 1 to 10. And then you just do the number divided by 8, take the ceiling, add to the result, and return it. And here's a one-liner if you want to do a one-liner as well. So you just take the ceiling of I divided by 8 for I in range. So basically the same thing, written as a one-liner. Either one is fine. And if you write a sum this way in Python, it will give you a generator, so this doesn't actually make a list. So they're both equally efficient. So we can submit this, and this should be good. And yeah, and everyone's runtimes are kind of close, so you just run it a few times and it's like roughly the same as everyone else. So yeah, that's basically that one. Now let's look at the second one and the added constraints. So the first problem, you only had 26 characters maximum, and you had lowercase English letters, and they were all distinct. And the idea is, like I said, you just put all your characters on every letter until all of them are filled up. Then you put them all on the second index, then on the third index, and the fourth index, and that makes all of your operations to push each button as close as possible, and it spreads it out as much as you can. Okay, so let's look at the second problem, and here it is here. Like I said, it's very similar. We're just one added condition. So before we had, let's actually make it a little bigger still. Yeah. Okay. So before we had only 26 characters, and now we have 10 to the 5th characters. So obviously we're going to have repeated characters. So you can see from these examples, nothing changes, except now you can have repeated characters and you just have a bigger word. So the strategy is still the same, right? You want to minimize like the index of every single character, but now there's another basically thing that you need to add. So because every single character has a count, they're not all treated equal. Like before, what we did is it doesn't really matter what character you put on every index because every character only shows up once, right? So for example, to push because you only have one Y, it takes one operation to get a Y, and you have one I, and it takes 2 operations to get an I. It doesn't matter. Like, it doesn't matter what character you put on every single one. But now, every character will have a count. So it does matter. So, for example, here, let's say we have, I don't know if they tell you, so you have a repeat of X, Y, Zs. So here you have 4 X's, 4 Y's, and 4 Z's. So in that case, if all the counts are the same, we can basically use our old strategy of let's just put everything on the first index and so on, and you don't have enough letters for that to matter, right? So you can just say like, we can just put X on the 2, we can put Y on the 3, and then we can put Z on the 4. Each one of these operations will take one click, and so the total is going to be 12, right? Because you have 12 total things, so you just get 12. But now let's look at this example, and this example is going to be a bit more interesting. So here let's write down our letter counts. So here for A we have 2, for B we have 2, for C we have 2, for D we have 2, for E we have 2, for F we have 2, for G we have 2, H we have 2, and I we have 6. And let's actually change some of these just to make it like a little bit more interesting in problems. Instead of having 2 of everything, let's just say these have 2, these have 4, just to make it a little bit more interesting. And these have 6. So the idea is still the same, right? We still want to ideally put, like, if we have all of these numbers, like let's say we still have our 2 through, we can actually probably even copy that ideally. So let's copy this over, and we'll just get rid of letters. Okay, so here is our like phone numbers that we have. Same kind of thing, right? The things they represent. But now let's actually change some of these. So let's get rid of these, and let's figure out like what needs to go where. Because now the letters aren't equivalent. And a really easy extreme example is like, let's say I have 1,000 A's. Like, let's say I have every single character A through Z, but I have 1,000 A's and 1 of everything else, right? So I have 1,000 A's and 1 of B through Z. Well, I would never want to do something like, let's put B here and then maybe like A here, right? I really want to make sure my A is the cheapest. So because A occurs the most, I really need to make sure that A is on this like first column, because that's going to be everything on the first column takes one operation to push. So I really need to make sure A is here. But if everything else is 1, then I can just move it normally. Like, it doesn't, the rest of the order doesn't matter. I can just do it backwards if I want to. I can put everything else wherever I want. So I can literally do like B, C, D, E, F, G, H. It doesn't really matter because these are all equivalent, right? H, I, J, K, all the way down, all the way down, all the way down. I still want to make sure that like they are spread out like this, but now basically you add one more dimension, and that dimension is how many times the number occurs. So now the only difference here is before we didn't really care like the order, but now we do. So we basically want to, what we want to do is instead of, like, we don't really care about the letter, but we really care about how many times does each letter occur. And so what we can do is we can get the count of every occurrence of every letter, and then we can just sort it in reverse order. And so what that's going to look like in this case is we're going to have an array. Like I said, the letter doesn't really matter. Like if we had 1,000 A's and the rest and every other character from B through Z was 1, or if we had 1,000 Z's and every other character was 1, like that would be the exact same solution, right? So all we really care about is the count. So we're going to take these counts and we are going to store them in reverse order because we want the biggest count to be put into the first row, right? So we're going to have 6, 6, 6, 4, 4, 4, 2, 2, 2. And now, basically, the rest of the code, the rest of the code is going to be very, very similar to what we had before. So we can still do that same loop where we just loop from the index, but now instead of looping from the index of the word, we're just going to loop through these counts. So we know we have 9 different characters, and we're just going to loop through all of these counts and figure out where the index is in the array. So let's index these as well. So, and let's make these one index. So this will be like 1, 2, 3, 4, 5, 6, 7, 8, 9. And now for these, we're basically doing the same thing we did before, except now we have our letters sorted by the count, because we want the letters with the biggest count to be inserted first. That way they can go into like the good slots, right? The first 8 numbers will go into the best slot, and so we want the numbers with the highest count to go there because the number of operations for those is only 1. So what's going to happen here is we're going to put in whatever letter has this count 6 at here, let's say. It doesn't really matter in which order you put it in now. Like, it doesn't matter if I put the letter with a count 6 here, or here, or here. These are all equivalent. These are all one operation. But I do need to make sure that they get put into the first available column. So basically, we're going to put in a letter with a count 6 here. We're going to put in a letter with a count 6 here, letter with a count 6 here, letter with a count 4 here, letter with a count 4 here, count 4 here, count 2, count 2. And now we are done with like the first column. So the next one will go into here. So as you can see, this is very similar to the other problem, except now you have a count. So instead of looping through letters, we will just loop through all of these counts, and we're going to do kind of the same exact problem. So we're going to have a result variable, and then we can still loop through all of these. So loop through counts, and then for each count, like how do we figure out what's the exact cost of the letter is? That still is this exact same thing, right? You take this one index. So take one index and do the same thing, right? So we do a ceiling divide by 8 to figure out what row is it in. And then we know exactly what's the cost of it, right? So for example, if this, like the first 8 elements here will be at index 1, so the cost of all these is 1, and that's what you'll get, right? Like 1 ceiling divided by 8 is 1, and so on, and then this one is going to have a cost of 2. So you just figure out like what's the cost of my letter. The letter doesn't matter, all you care about is the count, and then you just multiply that by the count of the letter. So in this case, you will say, okay, the cost of my letter is whatever this is, 1, and I'll just multiply it by 6. And you add all those together. So it's very, very similar to the first problem, except now you just, instead of like looping through I through the length of the word, now you just get the count of every single word. You sort it in decreasing order, and then you just take the index of the letter or index of the count divided by 8 to figure out like what column is it in, because each column has 8 elements. So you just figure out like what column is it in, and then you multiply it by the count of the letter, right? So for example, if G occurs 6 times, we know that G is going to be in the first column. It's going to be one of these 6s. And so the cost of G is 1, and it occurs 6 times, so we'll multiply by 6. So for G, the count of pushing all the G's will be 6. and you just add all these up. So all of these G's will have a count of 1 because they're over here. So this will be 6 total, 6 total, 6 total. Then all of the 4s are also in column 1. So this will be 4, 4, 4. And then for the 2s, 2 of them are in column 1. Doesn't matter which one. You can put them in however you want. And the next one's in column 2. So 2 of them will have a total cost of 2. And the one that's in column 2 will have a cost of 2 to push. And there are 2 of them, so this will be 4. So you just add all these up. So this is 18, 20, 28, 30, 36. And that's basically it. So I think this is actually one of the easiest third problems for the contest that I've seen, like at least out of the ones I've done for the last month. I think this is like very easy because it's very relevant to the easy problem. Like it's almost all the same. You just have to recognize I just need to sort them by priority by the count. And then I need to make sure the items with the biggest count get inserted into the first available column first, because those are going to be the cheapest. So we can look at the code there. Also very, very similar. So for what we want to do is for the word, we want to get, like I said, we want to get, that's not relevant. Okay. So what we want to get is we want to get the values, right? Like in this picture, we want to get the values for the count. So what a counter will do in Python is it will give you a dictionary of every letter and its count. Then we just get the values because all we care about is the counts, and we want to sort them in decreasing order. So you just do reverse equals true. So now we'll have the frequency of every letter in here in decreasing order. Then we have a result variable, and we do the same thing. So we loop through everything in the frequencies, and we add. So remember, we want the one index. If we look here, this needs to be one index. So we take whatever index it is, one index it by adding 1, and then we ceiling divide by 8 to figure out what's the actual cost of pushing that letter, and then we multiply by the frequency of that letter. So notice we're not using the letters at all. Like the letters are irrelevant. All we need to know is the count of each letter, and then you just return. And there is also one liner here if you're curious about that. So you basically just make a generator again. You take the index plus 1 divided by 8 multiplied by the frequency of that index for every index in frequencies. So either one of these works, and they're basically equivalent. Yeah, so we can submit this too, and you can see it's pretty good. And let's say I comment this out, I can submit this too, and it'll be roughly the same. Oh, I still need this line here. So there we go. Okay, and so now let's quickly go back and do the time and space for both of these. It's going to be very similar. So for the first one, essentially, we are just looping from 1 to the length of the word, but because this is only length 25 or something, it's going to be really fast, right? So we can just say it's O of n, I guess, technically. But since it's only 25 characters or 26 characters, it's going to be, you can say it's O of n, you can say it's O of 1, personal preference there. And space is O of 1. And for the second one, so now we have a bunch more characters. So our time, because we have 10 to the 5th characters this time, so if we go back here, we have 10 to the 5th characters. So this is going to be O of n too, but it'll just be longer. So this part, because still you only have lowercase English characters, this counter will have every letter from A through Z max. So the number of values in here will only be 26 maximum. So this whole thing is O of 1 basically, because anytime you have a dictionary of letters, it's going to be O of 1, because especially if they're all lowercase, because your word can be a billion characters, this can still only be 26 characters. So this part is O of 1, so this isn't like n log n or something. And realistically, this part is going to be way longer, right? Because this is 10 to the 5th. So sorting 26 letters is like 26 times log 26, which is like 3, or maybe not 3, but like 5, or 4 and something, which this is like way longer. So it's O of n for that. And then looping through all of the frequencies is also very fast. It's basically negligible, right? So because you only have 26 characters, this part will only be O of 26, which is just O of 1. And the space here, like I said, we're going to say it's O of 1 because this dictionary can only be 26 lowercase characters, no matter how big this is. Yeah, so I think that's going to be all for these two problems. I definitely decided it would be better just make one video for both problems because they're very similar. This is like a pretty easy constraint in my opinion. And actually, when I was doing this first problem, I didn't notice that it only had 26 characters. So I immediately thought of like this counter solution and then noticed it was even easier than that. So yeah, once I figured that out, like it was kind of natural to figure out what goes on here. So hopefully this was helpful. And if you have any questions about this, and if you do like this format where I do, this happens a lot in contests where like one problem is basically the same as another one, and I might start doing those in one video. So let me know what you think about that. And then I think there is 2 other problems left, which I haven't done yet. So count the number of houses. I think these are literally the same problem, except once again, the hard problem just has higher constraints. So I will do those. I'll probably just do the solution to the hard problem only, and then you can copy paste it into the medium one. Yeah, and so that's going to be all for this one. So hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.